Welcome back. So, we are studying NPTEL course on topological phases of matter, and we are now studying model Hamiltonian, and we were at one dimension in a lattice called Schrieffer-Heeger model, and what we found last time is that with a lattice with two sublattice of carbon atom, which we denoted by A and B sublattice, and with the hopping from A to B within the lattice being T, and with the nearest neighbor lattice from A to B calling T prime because the bonds are different, we arrived at this Hamiltonian. Okay. And then we said this, but there was a typo, and let me correct this typo. It turns out to be an important one, although the final result that I discussed are essentially same. So, the bracket was not here, but here. So, it is actually T plus T prime cos k a, and A is said to be 1. The lattice constant, and the other part, the imaginary part, remains the same. So, that gives me D2 being the imaginary part of the off diagonal hopping remains the same. It is the D1 part, again I removed the bracket from here and put it here, and that gives me this condition which remains the same. There was no typo here. Okay. So, then the condition is that T by T prime has to be less than the mod of it less than equal to 1. If they are greater than 1, you never achieve D1 to change sign within the Brillouin zone. D2 always change sign, goes to 0 at k equal to 0 and pi plus minus 2, and D1 would not change sign if this condition is not satisfied, and that is how the topological phases arises. So, we have drawn this phase diagram as a function of T by T prime. So, this is the region in which T by T prime is less than minus 1. So, that means we never achieve D2 never changes sign, D1 does change sign, and the band structure will not have a band touching point, and so the valence band and conduction band will be separated. So, this is an insulator and this is a trivial insulator. Okay. Now, something interesting happened when T equal to T prime, T equal to minus T prime. Remember this expression. So, D1 now is, you can take T out. So, it is 1 minus cos k, and that term goes to 0 when cosine equal to plus minus pi. So, when, and this is the point where D1 also goes to 0. So, that means you will have a band degeneracy. So, D goes to 0 and eigenvalues are proportional to plus minus is equal to plus minus D, the magnitude. So, D1 goes to 0, D2 goes to 0, so D also goes to 0. So, you will have band degenerate point. Now, as we cross to region C, now both D1 and D2 changes sign, but not at the same point. Okay. So, D1 is changing sign here, and D2 is changing sign at some value k star that we can find out from here. Okay. When this condition will be satisfied, T1 will go to 0. From there k star we can find out. So, what is happening here is that as we start from any point, and for the Brillouin zone we can start from k equal to minus pi. So, we are here, and as we wrap around, so here then d2 goes to 0, but d1 does not go to 0, and this is this point. So, this will be then minus k star, and this will be then plus k star. Plus or minus would not make much of a difference, except that it will just give you a different winding. Okay. And then again you go to k equal to 0, where d1 goes to 0, but d2 does not go to 0. Sorry, it is the other way, I made a mistake again. Minus k star, where d2 goes to 0, plus k star. Okay. So, you start from here, d1 goes to 0, then d2 goes to 0, then again d1 goes to 0 at the middle of the Brillouin zone here, and in between the band inversion has happened. Okay, as d changes sign, you see that this eigenvector will go from 1. So, it will change from 1 to e to the power I phi, and then it will become I phi, which is through the normalization, then this will become 1. Okay. Just plot the orbital weight with some Python code, you will see that. Okay. And then we come here, and then again we go here, this will be this point, it changes sign to this point. So, now because phi now wraps this degenerate point, despite the fact that the band has not really gone through the degenerate point. In this case it went through, but here it did not, but it wrapped around the degenerate point, and degenerate point is where the monopole is sitting. So, we rarely have not realized a monopole, but we wrapped around the Dirac monopole or Dirac point. So, this is still an insulator, and this is the non-trivial topological insulator. Okay. So, gamma is equal to half d phi. So, d phi now changes by 2 pi. So, gamma becomes pi, the Bery phase for the filled band, and for empty band it will be the opposite, because whatever is happening here, it is exactly the opposite is happening here. So, the Bery phase for the upper band will be plus pi, minus pi. Now, let us go to here at this point. So, at this point you can show pretty easily, and let me leave it for you to check. Again you will have a Dirac point, but now you can almost anticipate where the Dirac point will happen. It will happen at this point. So, this point is sort of closing in. So, let me draw it with different color. And I am not drawing all the way to here. I mean here it will bend. Okay. All right. So, now what happens is interesting. Now, let us go to E. Sorry, I think this is C. D, sorry, that was D. Is greater than 0 but less than equal to, or let me not do that, yes, E. So, again it is pretty easy to show that you will have a band inversion and it will go through both D1 and D2 will now also change sign, and in the band structure rather what happens is interesting. So, now there will be again some point where the band inversion is happening, let us call it K star, again K star. Now, the band inversion happening in the reverse direction. Okay. So, they are continuous, so do not go by and they will not touch because this is the zone boundary, again it will start something of this sort happen. So, this is again non-trivial topology. Topological insulator. This is Dirac Semi-metal. Why it is not called a metal rather semi-metal? Because the carrier density will be very low, because there is only one point at the Fermi surface, only one Fermi surface point. So, that is why these are semi-metal, this is topological insulator. But now what is interesting here is that if you actually track down where the band inversion is happening, you will see that you are wrapping it in this direction, whereas here we wrapped in this direction. We explained everything here. You start from any point in the zone boundary and you track down how this loop is wrapped, and here you do the same thing, you will see that you are going to wrap in the different direction. So, that means for the same lower band the Bery phase will now be -1 and the winding number, which is 1 over pi times the Bery phase, will now be -1, whereas here the winding number was +1. Okay. It is needless to say what will happen, and I will just leave you to figure out. Here again the band touching will happen around this, but with different color. Now this will be red and this will be blue, but the band touching will happen here, and as we go here again it will become trivial, the entire band structure will change. So now we have found this is winding number being 0, +1, -1, 0. For the negative band, for the band below the Fermi-level. So, we had 0 goes to 1 goes to -1 0. So, these are the topological insulator with winding number -1. This is also topological with winding number +1. And here these are trivial insulator. This is also trivial insulator. Trivial means which are, it is a mathematical term called topologically trivial, but for us it is just a insulator without any winding number. Okay. And what is happening in this region is you are getting a band crossing with a degeneracy, Dirac cone at k equal to ±pi, Dirac cone at k equal to 0, Dirac cone again at k equal to ±pi. So, every topological phase transition going from here to here, they are topologically distinct, and how we have made it distinct, it's not that the k space we have changed, it's within the k space with in the d space whether we have a winding or whether we are going through the Dirac monopole sitting at the d equal to 0 at the center. Okay. And if you are wrapping it around, it is like this Aronov bomb effect. We don't, the electron don't see the electron. This was like some magnetic monopole is sitting here. The electron does not see the magnetic field, and here also it does not see that Dirac point, but it goes around it. And when we go around a singular point means kind of a hole in our d space, in our Hamiltonian space. So, now what we have done is that we have created a hole in our topological space, and here the topological space is in the Hamiltonian space, and that is how we are changing the topology. And when we have a hole and we are going around it, we cannot describe such a system with just one chart or one gauge field or connection. We need at least two of them, and it is the difference between those. So, in fact, you can also do that, you can compute the connection and you will see that it will be, let us say, A minus, and this is for the A plus for a given band, and it will remain the same. But now as we go here, it will, so connections are not well defined at the Dirac point, there is a singular point, right. So, these are things are not well defined here, but what will happen here is that it becomes A plus within the given band, and then it changes to A minus, and here it is A minus, and it will change to A plus, and it is A plus. Okay. So, as you go across the Brillouin zone, and we have some k star point, this is 0, this is minus k star, and for the lower band in this region we have A minus gauge field, a connection is required to define the covariant derivative, and in this region you need for a given band, and for the other band it will be the opposite, and it is the difference between them that is this one. Okay. We will do this, do the explicit calculations in 2D. For 1D we have done it already earlier. You just see there is just the difference between them is just A1 minus A2 or A plus minus A minus. Okay. And here it will be the opposite. All right. So, we have now a good understanding of how a topological space is created in the Hamiltonian parameter space, and how that is linked to band inversion, and how we can tune it by changing the hopping between the two sublattices in a SCC's model in 1D chain. Okay. Now, we will do most of this stuff in 2 dimension and with few more additional details. Two dimension, and we will talk about semi-metal, Dirac semi-metal, and Chern insulator. Okay. And we already talked about these two phases here, Dirac cone and Dirac semi-metal and topological insulator. For 2D, instead of winding number we have a Chern number. So, that is why they are called Chern insulator. All right. So, now we will put back all three, D1, D2 and D3. Okay. We will come back to take an example of specific form of those, but let us go back to what they were, and what we can do is, let me see if I have okay. So, we will again set D0 to be 0. So, D1, D2 and D3, this is one would write, and the eigenvalue will be what we just talked about. So, what we now do is that we just define the unit vector and write it in terms of the polar coordinate, okay. And we know that dx generally, as we go from the Cartesian coordinate to polar coordinate, we define it with sin theta, cos phi, these are the two Euler angle, sin theta, sin phi and cos theta. So, in the D space any point is now and we want to stick to D constant D, which will give you a radius, and then you will have the polar coordinate theta will be with respect to D3, D1, D2 theta and phi will be the azimuthal angle. Okay. And we also have talked about that the 2D Brillouin zone with this direction being identified, this direction being identified gives us the torus, and now this torus is homeomorphic to S2 in the Hamiltonian parameter space. Okay. And you can see the eigenvectors that we wrote earlier. Now, if you put all these angles, we can write it in terms of this polar angle. This is for the plus band and this is for the minus band. Okay, so let me remind you, E plus minus is equal to plus minus d when d0 we set it to be 0. Okay. Here. Okay, and let me also remind you that this is cosine theta by 2 and some phi a orbital a plus sine theta by 2 e to the power I phi. So, these are the eigenvectors, and if you take any point it denoted by, so it will be, say, an eigenvector will lie here. So, if u plus lie here on the Bloch sphere, it is pretty easy to show that the E minus will lie at the antipodal point, the opposite. Okay. And these are the north pole and this is the south pole, and north pole is when theta equal to 0, and if you plug it theta equal to 0, you see that this term goes to 0. So, that means this state collapse to this state will collapse to phi 1 and u2 will collapse to phi 2. So, that means at north pole orbital 1 state lies and at south pole orbital 2 state lies, and the eigenstates are depending on the parameters which will dictate theta and phi value, the two eigenvectors will lie in the antipodal point. Okay. There is also a fancy way to do this called Grassmannian, but we are skipping those. Okay. And then if you compute the connection for minus band, which is this expressions, and we will get this. In fact, let me write this. So, we get, let me, okay, let's we derived it earlier. 1, 2, 3 and mu is equal to kx or ky. It is a derivative in the momentum space. And then once you substitute, you will get the choice of gauge. So, you can probably even show that it will be and what will happen for A plus, it will just be a minus sign here for A plus. Okay, so let me erase it, but let me remind you where have you seen it. You have seen this in the case of gauge field in the Aharonov-Bohm phase. We showed that the gauge field, if I think of a 2 dimensions, then the gauge field was only given by this term, but then if you assume that the electron is moving in the equator in a 3 dimensions, then if you want to cover the 3rd dimension with an angle, we found that this was the gauge field, which is defined. Now, you see an interesting part. This is only defined finite when this term is non-zero, and this term is 0 when with theta equal to pi. So, that means this term is cannot be defined in the south pole. So, this is only defined in the north pole. Now, so then what will I do? I need to define another gauge field for the south pole, in which I will have a minus sign. So, that will be defined in the south pole, not in the north pole, right. And the difference between them, this term will go away and you will left with this. So, in 1D we did not derive it because it is sort of very easy to obtain that if you put theta equal to pi by 2, which is where the 1 dimensional D1 and D2 lies, these terms will go away and you will only have this term, half of this, and for the other one it will be minus of this, and so the difference of the gauge field will just be the winding in the D1 D2. But now we are in 3D. So, the winding is now defined in a Bloch sphere. So, what is this winding? It is just a solid angle. And how do you see that? We compute the Bery curvature. In fact, now I will go to mu nu. It is taken from some notes which had a different notation. Okay. And we identify this, and if you write in terms of D, then we identify that this is nothing but the, okay, this term is rather nothing but the solid angle in theta and phi, right. And this term is becomes singular when D goes to 0, and when D goes to 0, when D1, D2, D3 all 3 goes to 0. But one more interesting thing happens is that this guy can go to 0 when D goes to 0, the connection also becomes ill defined or singular, but in another point it becomes singular is when D not equal to 0, but D equal to D3, which is nothing but this point, and when D goes to minus D3 it will be this point. So, this point corresponds to D equal to minus, or maybe it is the other way, and this is D equal to D3. So, south pole and north pole lies at D equal to plus D3 and minus D3. Okay. And then the Bery curvature is just a line integral over the interbrilliant zone, and that can be converted with Stokes theorem into a surface integral over the interbrilliant zone. So, we will have the Bery curvature, and that is our Chern number, which is the total solid angle over this entire space. Okay. So, now we are talking about a 2 loops or a surface integral, and if we wrap the D equal to 0, then we have a topologically trivial one with Chern number +1, and if you wrap it in the reverse direction, so it is like kind of a surface integral over this entire Bloch sphere, but with a surface being pointing inward versus outward, then we will get a Chern number which is -1. And these two are very analogous to what we did for the loops going in clockwise or counterclockwise. Okay. So, now let us take an example. Okay. So, let me not repeat everything, but the essential things. That is A and plus minus mu is equal to 1 by d, d plus minus d3 square root and epsilon a b dA mu dB, okay, which is equal to sin square theta 1 plus cos theta plus or minus, okay. And as we said, the difference between them, these things cancel, so we will be left with 1 by d1 square plus d2 square AB dA mu dB, which will just be equal to so with you can cancel it, and what we will have is phi. This two term will cancel, 1 minus cos square theta and sin theta. So, this is that. So, now you see this term is only looking at the winding on through the equator. Now, both the north pole and south poles singularity in A are removed, the subtract off, and you will only have a well defined quantity. Okay. And what we are measuring in Chern number is 1 by 2 pi. So, if there is a band inversion such that this is true for 1D and 2D, as we are doing the line integral, and we did it for 1D. For now in 2D, if there is a band inversion at some point K star contour such that inside, let us say it is plus for a given band and outside it is minus, and it is sort of going through this band inversion point, and that will be equal to it is actually just wrapping around the K star d phi equal to plus minus 1. So, eventually it just depends on this 2D Brillouin zone where the band inversion is happening. Okay, you just have to wrap it up. Okay. And just to draw it again, this 2D zone, and that gives us a homeomorphism to wherever this band inversion is happening, that point corresponds to this point. Now, you can say that I can choose a parameter in which the band inversion might be happening here, and that would correspond to somewhere here. So there is something beautiful about the topology is that we need two charts, one that covers south pole north pole but not the south pole, the other one that covers south pole but not the north pole. But it does not have to be that one has to be defined from the equator to the upper hemisphere and the other one has to be equator to the downsphere. It does not have to be. You can start from any point, just this one you can take as your chart and this one will be the other chart. The topology will remain same, because as you can see that all these informations are gone, it only depends on the winding on the phi plane, which is the phi. It does not matter at what value of theta this is happening, the theta drops out completely. Okay. All right. And yeah, so these are the state u minus, let me use it. So this will be the state u minus, this will be the state u plus, and let me also remind you that these are my orbital, and this is the point where d equal to plus T3 or minus, I guess, and this is the point where t equal to plus T3. Okay. So we identify, and this is where d equal to 0. So identify three special points in which things can go wrong or things can be ill defined. One is when d equal to 0, another is when d equal to plus minus T3. D equal to 0 correspond to the center, kind of a Dirac monopole, and d equal to plus minus D3 are the north pole and south pole, right. So special points. And the consequence. So the first one is, if I have a parameter space where d goes to 0 when d1, d2 and d3 all go to 0 at some k star, that can be a single point or a contour, we will talk about it, and then we will have a band touching or band degeneracy, where A is singular and F is also singular, infinity. Now this is kind of a Dirac monopole, right, because F is proportional to 1 over d, and here also it is proportional to 1 over square root of d. And we will identify them to be Dirac cone, Weil cone and nodal line or nodal loop. The second case is d1 equal to d2 equal to 0, but d is not equal to 0, rather d is equal to plus minus T3, this point and this point, where the connection vanishes, one of the connection vanishes, the other one is not, but the difference is well defined. All right. And this will lead to insulator, trivial or non-trivial, called Chern insulator. So, now you can see again the same like condition. I need to, if D3 has only one value or same sign, if D3 has fixed sign, then only one condition is satisfied. So, that means you only have north pole and you do not have to go to south pole, and this will has only fixed sign, then this is a trivial one. So, you just need one chart and you are done with it. If D3 change sign means it must go to 0 at some point, that means D3 also goes to 0 at some k star, but not where D1 and D2 also go to 0. So, all three have to go to 0, but if they all go to 0 at the same point, you have a degeneracy, but if they go to 0 at different point, then we have a non-trivial or we have a Chern insulator. D3 change sign, that means D3 goes to 0, but at a different point than D1 and D2 go to 0, where in the first case D3 has fixed sign, so it does not go to 0. It can be 0, which is even a simpler one, but it can be fixed sign, that will be a trivial insulator. Okay. So, these are again the background of Chern insulators and band inversion, gauge obstruction, and we will take now particular model called Rice-Millet model, and we will demonstrate how different parameters lead to this condition versus this condition, and it will be very similar because you can see that even Chern number also depends on winding in the equator. So, that means eventually it will boil down to just computing the winding around where the D3 is vanishing, D3 goes to 0, okay, on the equator. So, we do not need much of a calculations anymore, but we will use a Rice-Millet like a simple toy model and demonstrate how a trivial to non-trivial band insulator in 2 dimensions is happening through a band degenerate point. Okay. We will do that in the next class. Thank you very much for your attention.